Hi, what's up everyone? In today's lecture I will go through nuclear physics. So, most people are taught this way of describing the atom. That the atom consists of a nuclei, the core, which basically is just protons and neutrons, and around that circulates electrons in different orbits. So, we know that protons carries a positive charge. Neutrons, they carry a neutral charge, and electrons, they carry a negative charge. So in the core you will find protons, these black dots, and neutrons, and they are arranged like this. So the only element where you have no neutrons are hydrogen. The only element where you only have one proton is hydrogen. And we know that like charges repel and unlike attract, which would suggest that the core of an atom would repel its inner parts. The protons in the core would repel. And the only element that could exist would be hydrogen, since it only have one proton. So something is up here. There's a force that presses these particles together, which forces them to stay in this state. So we know that the Coulomb Law, the force between two charged particles, is equal to Q1, Q2 over 4 pi ellipson r squared. R squared. So Q1 and Q2 is the charge of each of the particles that you try to measure. 4 pi is 4 pi, and then ellipson naught, and then you have r squared, which is the distance between these two charges. And if we decides to put in the values for the proton, you will get 2.3 newtons of force. So these protons would repel with 2.3 newtons of force. Okay? So if they repel with 2.3 newtons of force, what holds them together? It may be the gravitational force, which is the gravitational force is the gravitational constant g multiplied by m1 multiplied by m2 over r squared, where r squared is yet again the distance between the center of mass 1 and mass 2. And this gives you a very small number, 1.86 times 10 to the minus 36. So the gravitational force that supposedly holds these particles together is magnitudes smaller than the repelling force, thanks to the like charges. So what holds these particles together? Let's get a new page for that. So there must be a force that is greater than the Coulomb force. And there is. It's called the nuclear force. And we know for certain that when an element reaches around 100 protons or so, roughly speaking, they start to fall apart. So the nuclear force should be comparable to the Coulomb force when an element reaches around 100 protons. So let's plot a diagram that describes that in greater detail. On this axis and on this axis. On this axis I will have r, the radius. And here I will have the attraction, at, and here I will have the repellent, r, big R. So we know that the Coulomb force increases as r decreases. meaning that it should look something like this, roughly speaking. So the Coulomb force falls as a function of r squared. So if r gets twice as big, the Coulomb force gets 4 times as small, and so forth. And we know that the strong nuclear force needs to disappear almost when the r becomes close to the width of the nuclei. And by having this information, we can plot a new graph for attraction. It will look something like this, broadly speaking. You see, if you have two protons that get the protons in the core can only touch each other very slightly, because if the strong nuclear force were to be any greater, they would simply collapse them into each other. So the Coulomb force needs to be smaller than the strong nuclear force in the core of an atom, obviously, for it to keep together. So there are obviously 3 types of interactions that can occur in the core. You have proton on proton interaction, you can have proton on neutron interaction, and then you can have, of course, neutron on neutron interaction. And the nuclear force needs to act on each of these interactions somehow. But the question occurs now, how are we supposed to study the core of the atom? Because you see, light, visible light, has a wavelength, lambda, of just about 10 to the minus 6 meters, where the proton nuclei, or the core of the core of the atom has a width of around 10 to the minus 14 meters. So there are no comparable light wave that you can measure the core of an atom with. So you cannot simply just take a microscope and study the atom. You need to find another way, and that way is called scattering, and I will explain that to you right now. So in physics, we have a way of solving problems. When things do not work out for us, we simply just increases the energy and smashes things into each other with greater velocity. And that is exactly what we do here. We take a proton and we accelerate it, and then we shoot it at a target and see how it scatters. So there are a few ways to do this. I will explain the cyclotron way. So a cyclotron, how it works is that you have 2 D-shaped pieces of metal. And through these pieces of metal, you put a current through them. So you have the negative plate here and a positive plate here. And then you shoot a proton to these plates. And we know that a proton has a positive charge, so it will get attracted to the negative plate. And when it does so, the magnetic field here will shift. You will shift the voltage, so this will now become the negative side. So the proton will simply accelerate in a centrifugal motion. So the force for this field can be described as F equals B Q V, where B is the magnetic field, Q is the charge of the particle, and V is, of course, the velocity. Since this particle moves in a circular motion, you can then simply say that B times Q times V should be equal to mv squared over over r, sorry. Which, if you rearrange this formula, you will find that V is simply B Q R over M. And if you take the time for one orbit, t, that equals d over s, which then simply equals 2 pi r m divided by, of course, the velocity. Since d time is simply distance divided by velocity, and the velocity is, as we see here, bqr over m. And if you invert that number, you will find that you can arrange that formula as bqr multiplied by m on top. You just invert this this fraction, and that essentially equals, let me just arrange the camera for you. That essentially equals, come on, let the focus work. You see the r's annihilate each other, and you are left with 2 pi times the mass divided by bq, like that. So we know that the formulation for this is 2 pi m over bq. And as you can see here, there is no radius term. Since the proton accelerates, it will move into a greater orbit. So as the velocity increases, the orbit will increase, proportional to the acceleration. So for every voltage, you will have a given velocity. So each orbit will take the same amount of time. Since if you have a higher velocity, you will have a greater orbit. If you have a lower velocity, you will have a smaller orbit, and those two annihilate each other. So when you have accelerated the particle to max E, which for a proton in this case is 20 mega electrovolt MeV, you simply rearrange this particle into a tunnel and shoot it at a target and watch how it scatters. That is basically how you study particles. So let's get into more depth about what is the strong nuclear force then. So the new strong nuclear force is one of the four fundamental forces in the universe, and it is carried by the gluon. So depending on the radius of the force, it will act differently. If you watch the strong nuclear force on a small scale, around 10 to the minus 15 meters, you will find how gluons hold together quarks in order to build, for example, a proton, where you have two up quarks and a down quark. And binding these things together are the gluons, the strong nuclear force. And if you decide to observe this in a greater scale, you will find how protons and neutrons are held together in the core of an atom. So there is a rule to remember called confinement, which basically describes how quarks can never be alone. There will always be a pair of at least 3, or a quark-antiquark pair. So if you have, let's take a proton for example, 2 up quarks and a down quark, and you try to pull this up quark away, the energy that you would need to do that would increase the potential energy in the field so much that you would basically create an up quark anti-quark pair, which of course would annihilate this quark, and then the up quark that came to existence will join this proton again. So if you would be able to give this proton enough energy where this up quark would be forced to leave the system, you would simply just create an up anti-up quark pair. And these two would annihilate and this thing would go into the proton. And that is the basis of nuclear physics. Thank you so much for watching. Hope to catch you in a future video.